the lab already, hopefully. Can anyone sort of tell me exactly what it is we're going to be doing today? Just sort of in broad strokes.
We're going to be using a scale to measure like density and volume.
Mm-hmm. What's the point of this exercise?
To determine like inaccuracies, I think.
Yeah, basically that's exactly it. Whenever you're doing an experiment, you have to have some idea about sources of error. In fact, that's a really big part of writing a lab report. In the discussion, you should always make a point of saying what were the sources of error in this experiment and what did you do about it in order to make those errors as small as possible. So what we're going to learn today is that when you do measurements are just that. There's no such thing as an exact measurement. It's always subject to some kind of uncertainty. Like even when you're just measuring something with a ruler, you measure something that's a foot long. Well, is that exactly 12 inches long, or is it 11.9 inches long? Or is it 12.1 inches long? There's going to be some kind of uncertainty. Two people looking at the same measurement will not come to the same conclusion about exactly what it is. So there's always going to be some sort of error inherent in any kind of measurement, and that's what we're going to learn today. Basically, that there are instruments that are specifically made to give you more accurate measurements than other instruments. For instance, what is this? Can anyone tell me what this is?
Graduated cylinder?
Yeah, it's a graduated cylinder. It's a little graduated cylinder. It's a 10 mil graduated cylinder. Oop. So if I were to measure, what would be better, more accurate way of measuring a volume of a liquid, in this or in this?
The graduated cylinder?
Yeah, definitely the graduated cylinder, right? For a lot of different reasons. One is that this thing is specifically designed to measure things, and this flask is not. This is not actually a measuring device. You do reactions in something like this. You don't do reactions in this. You measure liquids and then transfer them to something like this where you do your reactions. So we're going to learn about exactly how you deal with that kind of error, and you can actually measure error and then cope with it, because it's like I said, when you're doing an experiment, you need to know what your sources of error are, and if you can estimate what they are, you can basically give an idea of how accurate or how precise your answer is. Because giving an answer, if I ask you what was the mass of some object, and you said it was like about 10 grams, I don't really know how precise that answer is. It could be 7, it could be 13. I mean, I don't know how close that is. But if you tell me that it's 10.0 grams, I automatically know the precision of that measurement. I know that it's not 9.9, and I know it's not 10.1. It's 10.0. So I automatically know how accurate that is. So we'll learn how to do that today. So let me sort of get into what we are going to be dealing with today. Here we go. So just going to be learning about doing measurement and how to report and deal with uncertainty. So just the outline of the experiment. We're going to be looking at calculating experimental errors. And then this first experiment, we're going to be going over the steps of doing it, setting up the tables, and then how to report your data. Any sort of scientific theory or scientific law or whatever depends on the reliability of the data. Anytime you publish anything or you write a lab report or anything, you have to be able to justify how reliable your data is, or else no one's going to believe you. So like I said, if you publish something that, you did a chemical reaction and your yield was about 50%, that doesn't really have a whole lot of meaning. If you give exactly what the yield was and then explain all the reasons why it was precisely that and what the errors were, then people have a lot more confidence in your results, and they believe, basically will be more likely to believe whatever your conclusions might be. So there's a couple of different kinds of errors, and we need to be able to identify them. So one is something that's systematic. Now that's not a good one to have. What that means is that basically the way you're doing your experiment is wrong. There's something wrong with the way you're doing it, and it needs to be corrected. One thing that's classic is called a miscalibrated instrument. Anyone sort of give me an idea what calibration means?
Isn't it kind of like you're setting it to a standard so that everyone's measuring it by the same thing? Kind of like when you tear the what's it called? the balance, when you tear the balance.
It's not quite like tearing the balance, but your first part was absolutely correct. It's like setting a standard so that you know what you're measuring is accurate. For instance, let's say you develop some sort of newfangled digital thermometer that was like, super precise. And so you dip your, you say the temperature of my room is 25.49 degrees. It's like, oh, it's really, really precise. But you have no idea whether or not it's accurate. So one thing you might do in order to figure that out is by putting it first in ice water. What's the temperature of ice water?
0
degrees
Celsius.
0 degrees Celsius, right? Whenever you give an answer to a question like that, you have to have the number and the unit. So, right, 0 degrees Celsius, freezing point of water. So I take my newfangled thermometer that I just invented, and I put it into 0 degrees Celsius. And basically what I'm doing is because a thermometer, an electronic thermometer, doesn't know what temperature is. It's just measuring. It doesn't know what it's measuring. It doesn't know anything. It's just giving off a certain signal at a certain temperature. That's it. You have to tell the instrument at that particular signal, that is 0 degrees, because it doesn't know how to do that. So basically I put it into an ice water. It has a certain signal strength. And then I say, at that signal strength, that is 0 degrees. Then I put it into some boiling water. What's the temperature of boiling water?
It was 40 C?
Not 40 C, no.
100 degrees.
100 C.
100 degrees C, exactly. So that's precisely 100 degrees C. So I take it out of the cold water, out of the ice water, which is 0. I put it in the boiling water, which is precisely 100. And I punch into the thermometer, the signal you're giving off now, that is equivalent to precisely 100.00 degrees C. Then when I take it out and I measure the room temperature, it should be very accurate and very precise. If, on the other hand, I took that my thermometer and I put it into the ice water and it said it was -10, and then I put it into the boiling water and it said it was 90, obviously I'm off by 10 degrees. And so if I don't fix that, if I don't calibrate that instrument properly, every single temperature that I measure is going to be wrong. It's going to be off by 10 degrees. So that's what that miscalibrated, that's what that means. Because basically no instrument knows what it is measuring. It just knows it gives off a signal with a particular set of circumstances. You have to tell it, like a pH meter. If you're measuring the pH of a solution, like how acidic or how basic it is, It just gives off an electronic signal at a particular pH. It doesn't know what pH is. You have to tell it, well, at that particular signal, that's pH 7. This is pH 4. This is pH 10. And then you can measure it properly. So experiments with this sort of systematic error tend to be precise. Like this new thermometer can measure temperature to like 5 significant digits. Great. So it's very precise, but it's not accurate at all because it's off. So what's the difference between precision and accuracy? How can something be precise but not accurate? Someone give me a definition of precision.
Precision is like when the values are close to each other, and accuracy and the values are close to one true value.
Marissa, man, killed it. That's exactly right. Yeah, precision means that I get the same answer over and over and over and over again with very little difference. So for instance, if I'm measuring the boiling point of water and I get 90, 90.1, 89.9. Are those numbers precise or accurate?
Precise.
They're precise, right? Because I'm getting pretty close to the same answer every time. Unfortunately, it's the wrong answer, but I'm getting the same answer every time. So basically what that means is whatever method I'm using to determine the temperature is a good method. It's precise, it's reproducible, but there's something wrong. I haven't tuned it or tweaked it in order to give it the right temperature. So this would be precise, but not accurate. What about if I got numbers like this? What if I got 90 and 110 and 89.9 and 111? Would those be, and I'm measuring the boiling point of water, would those be accurate or precise or neither?
Neither.
Everyone jumps on the neither. Do you think this, it's not, well, we know it's not precise. That's pretty clear because it's jumping all over the place. This is off by 20 degrees. This is off by 21 degrees. This is off by 22 degrees between each one. So yeah, obviously it's not precise, but is it accurate?
No,
How come?
because it's not close to 100.
No, you were right and wrong at the same time. No one of those answers, no one of those measurements is close to 100. That's correct. But what if you average them? What would you get?
A 100.
Yeah, exactly. You'd get 100. So you can get accuracy without precision. It's rare, but it can happen. Basically, it means that, like for instance, in polling, you probably heard of, we're sick of elections and everything else and hearing about polling. But if you poll only a small number of people, your error when trying to look at a much larger population is huge. So if I only asked like 50 people who they're voting for, I could be way off. If I ask 100,000 people who they're voting for, that's probably going to be fairly precise and accurate. So something like this, where you have the average, that's something we're going to do today, actually, is measure something over and over and over again and see how precise versus how accurate it is. So this would be accurate, but not very precise. But of course, being great scientists like we are, we would like to be both, if at all possible. So now we look at random errors. So these aren't systematic. These are something that's just going to happen. We're going to try and make it as small as possible, but there's no way of avoiding these. For instance, if we're looking at, these are just errors resulting from from doing a measurement, like a person doing a measurement. Like if we're reading the volume from a graduated cylinder. So here's my graduated cylinder. What can I do measuring the volume of this graduated cylinder? What can I do to reduce the error as much as I can? What's like one thing I need to do?
Surface.
What about the surface?
Like having it on a flat surface.
There you go. Yeah, exactly. If I have it tilted at an angle, it's going to be very difficult to get an accurate reading. So that's one thing. Okay. Level surface. I like that one. So what's another one you can do? What's something else we can do to make it as accurate as we can?
Look at the meniscus.
Look at the meniscus, right? So be aware, meniscus. Be aware that like water has basically likes to attach to itself. It's going to have some surface tension, so that when I look at my graduated cylinder, it's not going to be flat, right? It's going to be a little bit of curve. So where do I read the volume from? From the top of the meniscus or from the bottom?
Bottom.
The bottom, right. It's designed to measure the volume from the bottom. Right, so we need to be aware of the meniscus. Excellent. What's another thing we can do? It's just as important as these other two. I'll put it this way. When you're reading it, where should you be in relation to the graduated cylinder?
Right in front of it.
Not only right in front of it, but where? Above it? Below it?
Level with it.
At the very same level, right? So it may look kind of silly sometimes. You see, people in the lab at the bench, and they're sort of getting on their knees and sort of getting down. But you got to do that. You've got to get right to the level of where that is, because if you're looking above, the level looks lower than it actually is, and if you're below it and looking up, the level looks higher than it actually is. So you've got to get your eyes right at the very same level wherever that meniscus is when you read it. So, yeah. So not only does the eyes have to be level as well. So you need to be at eye level. So those are three of the most important things when you're measuring the volume of one of these. Yeah, excellent. So when you present your data, so you've done your measurements, filled in the table, you have to give whoever's reading the report or reading your article or whatever it is, you need to be able to say how reliable and precise those measurements are. Because if, like I said, if you just say something is 10 grams, how many significant digits are there in that number?
1.
Just one. So basically all that means is it's not 1 and it's not 100. It's 10. And so it's basically to the nearest 10. It's not 0 and it's not 20. It's somewhere between 0 and 20. It's close to 10. That doesn't give me a whole hell of a lot of information. But if I measure the mass of something and it's 10.001 grams, I know immediately how precise and reliable that is, because now I have 5 significant figures. And I know whatever it was that you used to measure the mass of that can measure it with that kind of accuracy. If, on the other hand, you measure something that's 10.001 grams and you report it as 10, basically you've thrown all that precision out the window. So what we're going to do today is basically figure out how precise is the very first experiment, is figuring out how precise and accurate is the scale or the balance that comes with the kit. How can we rely on it? And we'll find out that by just measuring something once doesn't really give you a lot of information. You know, you'll get a measurement, let's say, of 10.001. But what if you weigh the same thing and the next time it says 10.007? And then the next time it says 10.102. And the next time it says something else. Well, that's great that it gives you this sort of precision, but that doesn't mean it's very accurate. So we have to be able to, by looking at the average of a lot of different measurements, gives us a better idea of the precision and the accuracy of our instrument. So that's like the very first thing we're going to do today, because that will come back into the second part where we're trying to figure out taking masses and converting them to volumes. So who's here has heard of standard error or standard deviation? Who's taken statistics? Anybody taken statistics? I would definitely recommend you take statistics. I took statistics like 35 years ago, and I'm still using it pretty much every day. You know, when I'm reading stuff in the paper with statistics in it, I know which ones are complete BS and which ones aren't. Anyone taking statistics? Nobody?
Yeah.
Anyone planning to?
Yeah.
So, Arissa, you've taken it. It's a good class, right?
Yeah.
Yeah, I use it. Like I said, I use it all the time. And like, you know, just learning how, you know, flipping a coin randomly. I flip it and it hits heads like 57 times in a row. What's the probability of it hitting heads the next time? Well, it's still 50%. People have trouble getting their heads around that, but that's, you know, stuff like that you learn how to deal with. So standard deviation and standard error are basically ways of telling people, I've collected a bunch of data and this is how precise it is. So without that information, we really don't know anything. So what I'm going to do is just go over some of this stuff. Presumably, if you have a scientific calculator, it will calculate standard deviation for you, because it's kind of a pain to calculate it by hand. But let's just go through it. So standard error. This just shows, this is just a group of numbers. So what all this is if I measure the same thing over and over and over again, what sort of distribution do I get in my numbers? So just under the curve here would be, under the curve here would be all of my individual data points. So basically it would just be full of all these data points. So if my data points are not scattered all over the place, they're in a very, very small window, it means I have precision. So this would be precise. It also is accurate because this is the real value that I'm trying to measure. And this is the average of all of the measurements I've made. So that is chemistry nirvana. It's both accurate and precise. Perfect. Under B, this is what I mentioned about having an instrument that is precise, but I haven't checked to see whether it's been calibrated properly. So for instance, if these are all be measurements of the boiling point of water, and they'd all be around 110 degrees. So they're all very, very precise and wrong. So that means I haven't, so would this be a random error or a systematic error?
Systematic.
Yeah, exactly. It's systematic, meaning I am systematically getting the wrong answer every single time. So my instrument is not the right, I haven't checked to see whether it's working properly. Now down here, this is where maybe I'm using the wrong instrument to measure something because I'm getting data all over the place. But if I average them all together, I wind up coming up with an accurate answer. So this would be like if I had like let's say some really old thermometer, and maybe, you know, and it's very hard to see, and it doesn't have lines in between. It only has lines for 90 and 80 and 100, and there's no lines in between. So it's really hard to estimate what the actual temperature is. So I'd get all sorts of not particularly accurate answers or, or precise answers. But when I average them all together, I've pretty much come up with the right answer. And then this last one, D, is the worst of all possible worlds. Not only do I have a crappy way of collecting data, it's also collecting wrong, crappy data. So we don't want to be doing this under any circumstances at all, okay? So that we want A is the perfect world. C is, we'll accept that if we have to. And D, we don't want any part of that at all. So this is the symbol for average. What's another word for average?
Mean.
The mean, exactly. So that is just this bar over it. You have the bar over it, that automatically means that's the average of all my values of X. So like, for instance, like I keep coming back to the boiling point of water. So X are my measurements of the boiling point of water. X bar would be the average of all of them. And you all know how to do an average. You basically just add them all together and then divide by the number of times you've taken that measurement. So that's fairly straightforward. Now, deviation is something we're going to be calculating today. Now, deviation just means with every measurement I take, how far is it from the mean or the average? This gives you an idea of precision. The less deviation you have, the more precise your measurements are. So basically, we just take the mean again, and for every point, we see how far is it from the mean. So we take the mean and we subtract each individual measurement. So deviation is of each individual measurement, not of the whole thing. So we can compute deviation for every single measured value. And that's something we're going to do with our scale today to see how precise it is. Now we're looking at, is there a question there?
Is the standard just like the average deviation?
Pretty much, exactly, pretty much. Let me show you. Man, queen segue. So standard deviation basically tells us about how much error we would expect in all of our measurements. It's kind of like the average, but not quite. So basically, so if this is all my measurements thrown together, basically what it is gives you an idea of how wide this is. So it's sort of, it's sort of like an underfed supermodel. You want your standard deviation to be tall and skinny, like hideously skinny. So, and we give it the just letter S, or sigma stands for standard deviation. So this would be better than this because the width is smaller, and that gives you an idea what the standard deviation is. And so it's no deviation at any one measurement, but like you said, it's sort of like the average. I'll show you exactly how you calculate it.
I think I'm in the wrong lab place. Is this Schoenberg?
Is this, excuse me?
Who is the lab? Where's the lady with the
Where's the nice lady? She's on, when does she do the lab? Well, she does it at the same time, but in a different Zoom room.
I cannot get her. I cannot get her. This is so frustrating. It makes me just want to drop the class.
So you can't find her link?
Yeah, I can't find anything. This class is also messed up. You can't do anything. It's like everything is online.
Yeah, well, unfortunately, everything is online for right now. There's not much we can do about that.
I got to drop this class. This is just frustrating. I can't be doing this every time. Thank you.
Okay. Bye. Oh man. So how do we calculate standard deviation? Comes up. So basically, you just calculate all the deviations together. So we know how to do that. So each individual deviation is measured, and then we square them, add them all together, divide by the number of measurements minus 1, and take the square root. So it's very close to the average deviation. It's not quite the average deviation, but it's very, very close to it. And so that gives us S. And so like I said, if you have a scientific calculator, or you can just go online, and there's probably a bunch of different places you can do. Basically, all you do is just punch in all of your measurements, and it'll spit back to you what the standard deviation is by doing this calculation for you. Because let's face it, this would be a drag doing this by hand. If you had 100 or 1,000 measurements, this would be kind of hard to do. But that's what the standard deviation means. And this is basically, in statistics, this is used to basically give you an idea of how accurate your measurements are. And so whenever you've heard, and you've probably heard, let me clear this out. You've probably heard when people are talking about like a poll, for instance. I'll go back to that. A poll is given, and it will say, you know, like 50% of voters think Joe Biden should be shot into the sun. Okay, what is that? How accurate is that? Well, then they say, well, it's 50% plus or minus 5, 19 times out of 20. What does that mean? I'll show you what it means. It means that 1 standard deviation, 2 standard deviations, that gives you what's called a 95% confidence level. So you can be confident that 95% of the time, the actual answer is inside this part of your curve. It's somewhere in here. So here's my 50%, and here's my minus, this is 5% to the left, and this is 5% to the right. So that's what that means. So the more and more measurements you take, the less and less your errors become. If you take only, let's say you only interview 10 people and 5 of them say that Joe Biden should be shot into the sun. Well, that means that your errors are huge. That means that you're probably, it's 50% plus or minus 50%. That's not very accurate. But if you asked 1 million people, that means that basically your errors shrink to they're really, really small. And then you would have 50% plus or minus 1. And if that's the case, then 95% of the time, the actual answer is going to be somewhere between 49 and 51%. That's basically what that means. Okay. Anybody have any questions about standard deviation? It's basically a way to tell us, I got this data. How good is it? That's really what it is. How precise is my data? And if I was to extend it out into the world and try and make a prediction, how accurate would it be? And the standard deviation gives us an idea of how accurate it actually would be. So this is, like I said, this is something that you could have your calculator, your computer calculate for you, but I want you to have an idea of what it actually means. So this is the standard deviation, this distance from the mean. And it basically, the smaller and smaller that is, the more confidence you can have in your data. So the relative standard deviation is just a way of turning it into a percentage. So this will be able to better give us an idea how we can compare one thing to another. Like for instance, if I'm looking at the error of my 10 mil graduated cylinder and my 50 mil graduated cylinder, if I say that the error in my 50 mil graduated cylinder is 10 times or 5 times more than my 10, that doesn't really give you that doesn't give you a really good idea of what's happening. Because the percentage error would probably be the same. And I'll explain why that is, because this is 50 mils, and each one of these, when you look at it, you can see that there are these tick marks for 49, 48, 47, and so on. And right on the top of the graduated cylinder, it says 50. You won't be able to see it. It says 50 and then colon 1.0. So what that means is each one of these marks is 1.0 or 1/50th of the total. Now, if we look at the 10 milliliter graduated cylinder, on the top of it, it says 10 colon 0.2. That means it's a 10 mil graduated cylinder. And each tick mark is 0.2 mils. So there's also 50 tick marks for each one on the cylinder. So the relative error for both of these is probably the same, even though the error for the big one is going to be about 5 times greater than the error for the small one. But because we're measuring 5 times less, the relative difference is pretty much going to be exactly the same. Okay, does that make sense to everybody? Since you're measuring something 5 times bigger, your error is going to be probably 5 times bigger as well, but relatively it'll be the same. So it's not fair to say that you get 5 times the error with this than you do with this, even though it's true. So a relative error is just looking at what should be the right answer and what we measure as the right answer. So for instance, going back to the whole idea of measuring the boiling point of water, we know it should be 100.0 degrees C. But if we measure it at 99.96 degrees C, and it should be 100.00 degrees C, then there's some kind of error in it. Well, the relative error is that difference divided by what it should be. So obviously we would like that to be as small as possible. And we're going to work that out today as well. Because what we're going to do is measure a volume in here, and then we're going to determine the actual volume. Anyone tell me how are we going to do that? How do we measure? So I'm going to put about 7 mils of water in here. And I'm going to look at it and say, okay, that looks like to be about 7 mils. How are we going to measure the exact volume of water in there? How's that possible?
By subtracting the volume of the cylinder.
Subtracting the volume of the cylinder? The cylinder doesn't really have any volume. I mean, because it's open. It can contain a certain volume. It's not the volume we're going to be subtracting.
Mass.
We're going to be looking at the mass of the water. Exactly. So by calculating the mass of the water that's actually in here, we're going to be able to calculate its volume. How are we going to do that? How do you measure the mass of something and then be able to calculate the volume of it?
Is it because we know the density of water? So
Precisely. Exactly right. Excellent. Yeah, because the ratio of mass to volume is equal to the density. And we know what the density of water is because, scientists have been measuring that very, very accurately for hundreds and hundreds of years. So that is actually a table that's in the lab manual. basically gives you the whole list of densities. You can also just look it up too if you wanted to. That's why we need the thermometer for today. That's the whole point of the thermometer, because we're going to measure the precise temperature of our water. So then we know what the density is. We'll measure the mass. We'll know what the density is. And if you know those two things, you can calculate the third thing. So we'll have our estimate of what the volume is by reading the volume off of the whatever particular measuring instrument we're using. We'll have that, our own estimate with our own eyes. And then we'll calculate what the actual volume is by measuring more precisely the mass and then using an accurate density. So that's how we're going to figure out what our relative error is in these things. Excellent job. So our first experiment. Obviously, I'm breaking a rule right here. What rule am I breaking?
No germs.
Mm-hmm. So I will move that away before I start anything. You're going to want a clean surface, obviously. You don't want to have like a whole bunch of dust or anything else. I'm going to have dog fur in my experiments, regardless of what I do. But, you know, what can I do about that? You don't want to have any food around. You may not want to have any kids coming up and bumping you on or pets bumping you in the arm, if you can avoid that. Are there any safety concerns for today's lab?
The water could spill on your lap. That's about it.
That's about it. Yeah, you could spill some water. Someone could slip in the water, but that's really about it. You still should have some, goggles on, but I'll kind of let that slide for today. But when we're dealing with chemicals, you're definitely going to want to have goggles on. There's no doubt about that. So like when we deal with something dangerous, any kind of chemical, I don't even care what it is, if it's salt, you should have eye protection on, okay? That's going to be really critical because we don't want any, and who's got contact lenses? Anyone wear contact lenses? Anybody? Nobody wears contact lenses? Dang. If you do, don't have them in when you're doing experiments. So I think probably my girl's chasing rabbits in her sleep here. Because contacts, basically, if you spill something in your eyes, the contacts, I think I probably mentioned it before, the chemicals will concentrate under the contact and actually prevent you from washing your eyes out. And so, yeah, it's extra bad having contacts in the lab. You definitely don't want to do that. All right, so hopefully we all have our kit. We have our 2 graduated cylinders. We got our balance. What's the Erlenmeyer flask? Someone hold up the Erlenmeyer flask for me. What's the Erlenmeyer flask look like? Not a lot of people with their cameras on, so I can see what you're up to. Who's got an Erlenmeyer up? Ronnie's looking for it.
Professor, what is it called again?
Lance, there you go. Yeah, Erlenmeyer flask. It's one of these. So what's the difference between a flask and a beaker? So this is a flask. What's the difference between that and a beaker? How would I tell the difference immediately? Lance again's got the beaker out. What's the difference, Lance, between the beaker and a flask?
With the beaker, it's not only bigger, but it also has the measurements on it, kind of like the graduate cylinder, so you're able to measure volumes of liquid in it as well. I think it's so anyway.
But how could you tell the difference between them from across the room? You don't even need to be close to it.
The flask, it has like a different shape as well. Like the beaker.
What's different about it?
Unlike from the beaker, it's like bottom half is like a bit more like wider to hold more volume.
Yeah, exactly. The flask has a narrow top. And it has a narrow top because generally we do reactions. When we do reactions, we do them in flasks. And so, like, we'll heat them, reactions will go on in there. And basically what we don't want is the stuff to come flying out of it. And so we generally don't do reactions in a beaker. If we do, they're generally like mild reactions, like we're dissolving something in water, something that's not too dangerous. It's not going to be throwing off fumes or splashing out of it. Whereas with a flask, it's designed basically to keep stuff from splashing out of the top. And so it has a really narrow, so the top is much narrower than the bottom. Beaker is the same on the top and the bottom. The shape is the same. And the other thing is, as Lance pointed out, if we look at the flask, it is not designed for measuring things. Because look, it basically has this 25 mil flask basically has two measurements on it, 25 and half of that, 12.5. So this is not a terribly precise instrument for measuring the volume of something. That's why we don't use it for measuring things. That's why we do reactions in this. We don't use it to measure things, like ever. Now, a flask or a beaker has all these gradations on it. And you can see the gradations on it. It is used to measure things. It is not, basically it's what you really use this for is it's basically for transporting liquids around. It's not really for accurate measurements. If you wanted an accurate measurement, this is a 250 mil beaker. If you wanted to accurately measure 250 mils, what would you use?
The graduated cylinder.
What kind of graduated cylinder? How big would it be if you wanted to measure 250?
I guess a 250 mil graduated cylinder.
There you go. Yeah, you would use you'd use a big ass graduated cylinder, either 250 or 500. You can get 500 mil. You can get 2-liter graduated cylinders. You can get really big graduated cylinders, and that's what you use for measuring large volumes when you need to have an accurate volume. I would use this if I don't really need an accurate volume. Like if someone said, I need about 200 mils of water, then that's fine. Use a beaker, fill it up to 200, and that's good enough. But if someone said, I need precisely 200 mils of water, then I would get me a 250 mil graduated cylinder, because that measurement would be a lot more accurate. If you don't need to be accurate, then this is fine. If you do need to be accurate, not fine. So we need a thermometer, our wax marker, 2 plastic cups. One thing that isn't on here, and I would recommend everyone go get it, is this. It's called a transfer pipette, and you have some in your kit. So you might want to go and get this, because for the simple reason, it is really hard to pour precisely 7 mils of water into this. It's basically impossible to accurately pour 7 mils of water into this without going over or under. And then you're trying to dump some out. Oh, that's too little. And you're trying to pour some in. Oh, that's too much. But what you can do with this is fill it with water and then put it in drop by drop. That makes it a lot. I'm surprised it's not on here, because it'll make your life much easier. So see if you can find it's called a transfer pipette. So you squeeze it. Here we go. You squeeze it from the top, blows out water. Then you let the water come up, and then you basically just squeeze it again to let it go out the bottom. So highly recommend it.
We just need one?
Yeah, just need one. Yeah, because we're only going to be using water today. So we'll just use the same one. If, on the other hand, you're using like 2 different solutions, then yeah, I would use two different transfer pipettes, because you wouldn't want to mix them up. Like if I had one for acid and one for base, I'd want to make sure I was using the same one. Okay, so distilled water. I imagine some of you may not have gone out and got distilled water. Can anyone tell me what distilled water is? What is distilled water?
Water that's been boiled.
Water with no minerals.
Not just that.
Just
It
pure
has been
water.
boiled, but that's not the finish of distillation. What else does it need? Yeah, it doesn't have any mineral. It does, well, a lot fewer minerals in it, certainly. But when you distill something, what does that mean? Boiling is one part of it, but there's a second part that's just as important.
Doesn't it like separate the molecules or something like that?
It does separate the molecules. For instance, if I'm making moonshine, and who here hasn't made moonshine? So to make moonshine, you use what's called a still, right? So so here's my still. And I've got in here what's called mash. So I've got my corn or barley or whatever it is. So the yeast is like eating it up, converted some of it to ethanol. But I can't go around, I can't be a respectable moonshiner because the yeast will die at around 15% ethanol. I can't sell 15% ethanol, I'll be laughed out of business. So what do I do to increase the concentration of ethanol? I distill it, but what does that mean?
Purify?
It means to purify. Yes. How? How am I going to be purifying it? Someone pointed out, I can't remember who it was, that you have to boil it. That's absolutely right. So I have to have a fire going on underneath. So I got my fire going. And so when I do have my fire going, I boil this. So it starts boiling. So now I've got fumes coming out. What do I do with the fumes? If I just boil it, the fumes are just going to go everywhere and I'm just going to be left with nothing. So I have to do something with those fumes. What do I do with them?
To hold them in another container.
So I transfer these to another container, right? So I just don't let them go out in the air. I capture them, I transfer to another container. And what do I do in the second container?
You condense it?
Exactly. How do I do that?
By lowering the temperature.
Bingo. Excellent. Yeah, that's all that means. Basically, I'm taking my ethanol, I'm boiling it. I'm turning the liquid into a gas. Now that I've got a gas, I need to turn it back into a liquid again. So I'm going from liquid to gas, back to liquid. That's distillation. And so why doesn't it this, when I'm boiling this, how come the water doesn't boil too?
Because of the density?
Hmm?
Because of the density?
Nope.
It boils at a lower temperature than water.
Yes, exactly. The ethanol boils at a lower temperature than water does. Ethanol boils at around 80 degrees Celsius and water boils at 100. So ideally, you would want to heat it just up to about 80 degrees and just let it sit there. That would be so the ethanol would boil off and most of the water wouldn't, but not all of the water. Some of the water is going to boil off because just because not all the water is boiling doesn't mean that some of the water isn't being converted to gas. We'll learn later there's a certain thing called vapor pressure. Even ice gets turned to gas. Have you ever noticed that if you made ice in the freezer and if you left it for like a year, there wouldn't be any ice left? Well, what happened to it? It all got turned to gas. Even at 0 degrees? Yes, even at 0 degrees. So you can't just do this distillation once. You would have to do it over and over and over. So some people generally, they distill it like 3, 4, 5 times. And by about the 5th time, you've increased the ethanol concentration to like 50, 60, 70%. So that's how distillation works. Yeah, so when we distill water, we boil it at 100 degrees, and then all of the salt and ions and minerals and, you know, dirt and whatever else that's in it basically gets left behind. Okay, yeah, so that's distilled water. If you don't have distilled water, filtered water is okay. If you've got a water filter in your tap, that reduces a lot of the carbon-based compounds in there, reduces a lot of the organic compounds in the water. It doesn't really get rid of a lot of the ions, but, you know, it'll be good enough. Some of the reactions we're going to do later, it's going to be important to have distilled water, because if there are other ions in the water, it may affect the experiment. For this one, not so much. But for other experiments, it very well might. It might interfere. You can get distilled water at the grocery store for like, you know, $1. So it's really not that, it's not that expensive. So for this one, not as important, but for coming up, it may very well be. So for cleanup, yeah, not going to be a problem today because it's just water. You can just pour it down the sink. So first part of the lab. So we're going to determine what the uncertainty is in our balance. So hopefully everyone has their balance. Mine looks a little different. I got a different lab kit. So mine is a small black one, but basically they all work pretty much the same. So notice that there's 3 buttons on it. There's an on-off button. Well, duh, that makes sense. There's a mode button, which basically tells you, do you want grams? Do you want ounces? Do you want grains? Do you want carats? And then this last one says tare. What's that?
It like zeros the balance.
Right. So basically, if I have my balance, then I put my graduated cylinder on it, it'll give me the mass of my graduated cylinder. If I then hit tare, it then goes back to 0. And any additional mass that I put in here in the form of water or whatever else, it will then register that. And so it's really helpful in, like, when you're weighing like a large volume, like let's say you want to measure out 50 grams of sodium chloride or something. Well, you get a beaker, you put that on the balance, you zero it, and then you just start adding sodium chloride till it says 50. It'd be a pain if you had to like constantly be doing math to like, what do I need to get to? What's the math? So to avoid that, you just hit tare. That's all that means. You're just resetting it to 0, and then any additional mass comes from what you've added.
I have a question.
Yep, go ahead.
How do you put the batteries in?
Yep, got to have batteries in there. I think sometimes the battery, in mine, the batteries were already in there, but they were wrapped in plastic. So I needed to take the plastic off. Mm-hmm.
How do you do it?
It's like you sort of have to like slide it out.
Slide it out?
Yeah, you just pull those to the side.
At the back.
I don't.
Yeah, press in with your thumbs and then pull outward.
Oh yeah, sorry about that. Yeah, it's like you have to like put like your thumb in between, like you see like the little the little indentation, like that's like closer to like the center. You kind of have to like put like, your thumb in there, like in between.
Okay. I'm probably just not lines, but I'll get it.
Did you get it open?
No, I didn't. I'm still trying.
Use these fingers and then.
Oh. Okay. Thank you.
Oh man, Arissa to the rescue! That's awesome. Yeah, it's like opening those child-proof caps. It's like it's sad. I can't do it a lot of the time. All right, so I'm going to give myself a little more room to work here. All right, so So you want to have this on a flat surface. That's really, really important. So that goes on a flat surface. You hit the power button, and then make sure you select, it should say G somewhere. If it says GR, that's actually grains, which is like a really old system of measuring mass. Then I think CT is carats, and OZ is ounces. So you want G for grams. So you should have two cups, and the wax marker is just for writing 1 on one of them and 2 on the other one. So you just tell them apart. Because basically, if we were to measure cup 1 and then cup 2, and we got different masses, and you were to blame it on the balance, well, it's not the balance's fault. What do you think the tolerance is in the factory that produced these for making them exactly the same mass? Probably not very high, right? I doubt that these are made to be within like 0.01 grams of each other. That would take a lot of work to make the difference so small that probably isn't worth it when you're just making plastic cups for a living. So you're probably not that worried about the difference. So the difference we see in the mass has to be within the mass of each cup. So we're going to measure 1 5 times. So we'll just put it on there. Now what you also want to do is don't write down the first number you see. You will notice it's changing. Why is it changing, do you think? What kind of mass are people getting?
9.38.
Wow, okay. I'm getting, let me write mine down. I'm getting 10.17.
I'm getting 9.95.
Okay.
I got
now
10.11.
we're all going to be different. Why? Because we're not all measuring the mass of the same cup. So like I said, these are not precision instruments. It's just a cup, right? You probably would see less tolerance in something like these, or like a more scientific instrument. These are not scientific instruments, it's just a damn cup. So one thing I want to point out about the table, notice that it has the units in there. That is essential. I'm going to jump on people for leaving units out of measurements, because a measurement without a unit is just a number, and numbers are useless. Numbers don't mean anything. 10 is a meaningless number. 10 grams, that tells me something. It means it's not 10 ounces, it's not 10 pounds, it's not 10 kilos. So you always, always, always have to have the units in here. So if you have the unit in the top of the table, you don't have to have it here. But if you don't have the unit there, you must include it there. The unit has to be somewhere, okay? So why do you think, now my number is like 10.20. Why do you think the numbers are changing? What's going on with the number changing like that? What could change the mass?
Dust.
Air?
Air, exactly. Just breathe in it. Just go. What happens? Changes pretty dramatically, right? So in the lab, when we're measuring the mass of something, we actually, in the balance, has a cover over the top of it. And you can probably make one if you had a box that you could see through, like a lucite box or something, and put the lucite box over the top. That would prevent air from moving around in the room. Just waving my hand over the top of it is changing the mass dramatically. So that is why you want to sort of wait and see what it sort of, when it stops changing, and then write it down. Because now mine is like 10.23. Now that is different from the 10.17 that I first wrote down. So when it finally stops changing and sort of balances out, take that number down. It may maybe wait like 10 or 15 seconds, and then let the the air currents stop moving. So we want to do that 5 times, and then report the mass, the average. So this would be the average at the bottom. So do it for cup number 1, and then cup number 2. And then we're gonna use that to figure out how accurate is our balance. Just because it gives us 5 significant digits, usually 4 significant digits. I think these go up to 100. So I think 99.99 grams is the highest they'll go to. Just because we can get 4 significant digits out of it doesn't mean we're going to get 4 significant digits of the mass, because there may be some error in there. And the other thing you should do, because right now I took my cup off and my balance says 0.11 grams. What should I do?
Push the tear.
Exactly. Tear it again. Because if I don't, that is an error I've put in there. That is a systematic error of my instrument that I didn't deal with. And even small things like if you're not wearing gloves and you're taking the mass of the cup, what else is on the cup that you may be taking the mass of?
The wax pen.
What's that?
The wax pen.
Yes, exactly. If somebody just wrote very slight 1, or if someone else just ground down and put like a huge 1 on it, yeah, the mass of the wax pen is something that needs to be considered. Excellent. What about your hands?
Sweat.
Sweat, oil,
germs,
protein, they're all being transferred from your hands to the cup. So the more you handle it, you may find that the mass increases over time. And that's because of you. There's more of you on the cup for the 5th measurement than there was at the 1st. So these are all things that you need to think about. So that's another reason why scientists generally, like when I worked in a biochemistry lab, I always wore gloves. And it wasn't because I was worried about the danger of what I was working with going into me. I was more worried about me going into my solutions. I didn't want enzymes coming off my hands and dissolving all of the stuff I've spent weeks making in the tube. So I was more worried about me becoming a problem with my solutions. So that's something else to consider. All right, so this one's fairly straightforward. Let's go to the next. Yeah, make a note of the unit. Yes, yes. So now we're going to figure out the uncertainty, because what we're going to do, we're going to measure the deviation or calculate the deviation from each one. Now we're going to have our average. So we'll have our average mass, and we would go, so that'd be our average mass of 1, cup 1, and that'd be our average mass of cup 2. So each measurement, each separate measurement, we're going to subtract from the average and get our deviation. So if my first one was 10.17, let's say my next one was 10.23, my next one was 10.24. If the average was 10.20, then I calculate each one of those deviations. And then I see what the average deviation is. That'll give us an indication of how precise these balances are. I'm kind of curious to see what people get. And see if your deviation is different. Would you expect your deviation of cup 1 and cup 2 to be the same or different?
Different.
Why is that?
Because maybe the amount of plastic used in each cup is not the same.
Now, the mass would be different. Yes, I totally expect the average mass to be different. But do you think the deviation will be different?
It's the same.
That's what I think. I mean, obviously we need to do the experiment, but that's what I would predict. Because the deviation doesn't come from this, does it? Not really. I mean, there'd be some deviation, like I said, like the more we handle it, the more mass we're adding to it. So yes, there's some deviation that comes from us, but mostly the deviation comes from the balance. How accurate and reproducible is the balance? So if we're doing them relatively at the same time with relatively the same mass, I would think, I can't guarantee, but I would think the deviation should be pretty much the same. That's, fingers crossed, that's going to happen. Okay.
Can I ask a question?
No. Yes, of course you can ask a question.
So for the average, do we account for significant figures? Because mine is like 0.002 in the deviation. So would that just be 0?
No. No.
So don't round yet. Don't round.
Yeah, we don't. Yeah, no, that's a real number. So okay. Yeah, that's not 0. So unless it's absolutely 0, and maybe your deviation is, goes up and it goes down, and when you average it all out, it comes out to 0. Then you could write down 0.00, whatever it is. But if it's an actual number, you can't just round that to 0.
Oh.
That's a real number. Yeah. It's important to know that number, because then it gives us an idea of, well, oh, wow, this is a lot more accurate than I thought. So it's good to know. So now we sort of get to the meat. Like, again, you don't have to rush along, and you can do these measurements later. Basically, what I want to do is sort of go through the whole thing and answer any questions you might have. You do your calculations later. Do your experiment now, and then do your calculations later. Do your measurements now, then your calculations later. So now we're going to figure out, so we need to figure out how accurate this thing is, because what we're going to be doing is looking at the uncertainty of measurements in our glassware. And we can't really do that unless we know the uncertainty of the masses. Because, like I said, we're going to be using the mass of the water to determine the volume, the so-called actual volume. And if we can't be certain about the actual volume, we certainly, can't be making any claims about our uncertainty in measuring it ourselves. So now we're going to need our distilled water, or filtered water, or tap water if that's the only water you have. Now, what's important here is that you don't just get cold water from the tap and then immediately take the temperature of it, and that's going to be your temperature. I have had my distilled water sitting in this glass for the last hour and a half. So that is the actual temperature of the water, because the temperature is going to change, obviously. If I took it out of the fridge and when it's at 4 degrees, well, an hour later, obviously it's not going to be 4 degrees anymore. And we need to know what the temperature of this water is. So you need to let it sit for at least half an hour. Okay. So does everyone have everyone find their thermometer? It will be in a square case that looks like this. The thermometer will be inside. It's really small. So you take it out, and obviously do not grab the thermometer by the by the bulb, because that will heat it up. Grab it from the top, and then you get level with it, and you try and give your best estimate as what you think the temperature is. I got to get real close to mine. It looks like 15, 16, 16.5. Yeah, I would say mine's like 16.5 degrees. And so remember, whenever you're making a measurement, that last digit is an estimate. That may be, let me repeat that because that may be a little surprising. So when you're measuring the temperature, so here's the temperature, notice that it's not going to be, it may not be exactly on one of the lines. It may be in between it. And so if it's in between it, here's my thermometer. Oh, what the hell's going on? Something's wrong. I no longer seem to have control of my computer. That's not good. Oh, it's because I splashed water on it. That's definitely not good.
I have a question. Is
Yes.
the top of the thermometer, or am I doing it the wrong way?
Yeah, the top has a little loop. There's a little loop on it. So you could like loop a string through it and then drop it in somewhere. Oh, there we go. Yeah, so this is the top. Don't let water splash on your computer. Yeah, so this is the top right here. You see that it has that little glass loop on it. And then this would be the bottom that has the liquid in it. So don't worry, this isn't mercury. This is just ethanol. Just some alcohol solution with some food coloring in it. So not dangerous. More dangerous that if it breaks, you like poke yourself with it. So we see that your temperature is probably not going to be exactly on one of these tick marks. And even if it is, it's kind of really hard to say exactly what the temperature is. So we need to do an estimate. So if this was, let's say 15, 16, 16.5. So if my temperature was like about here, I then have to, 15.5, duh. I have to make a determination of what I think that temperature actually is. So I know it's not 15. I know it's not 16. I know it's slightly less than 15.5, but how much less? That's really up to me. So I would say that's like 15.4. Somebody else might look at it and say, no, I think that's 15.3. Somebody else might say, no, that looks pretty close to 15.5 to me. So that's why we'll be working with partners. Generally, they will both look at the either the temperature or they'll look at the volume in something, and then they'll take an average of what they both report, because that's probably closer to the truth. But all three of these digits are significant. The 15 is significant, and the 0.4 is significant. And remember, the 0.4 is an estimate that I made. And that's true of any sort of measurement. Generally, the last digit is an estimate, but it's still a significant figure. So figure out what your temperature is, and we are going to use that temperature to figure out how dense is this water. Because what's the sort of accepted density of water?
1, right?
Again, I need units.
No, 1.
1 pound per liter, 1 kilogram per gallon. I mean, I need numbers. One is correct. That is, but 1 what? Anyone help him?
Gram
per
gram by cubic The cubic centimeter?
Yes. Or milliliter, it's the same thing. Cubic centimeter is a milliliter. So it's 1 gram per mil. So if I have 7 mils of water, I should have 7 grams. But it's not exactly 1.0. It's really close because it depends on the temperature. So the higher the temperature, the more the water molecules move apart from each other and the lower the density is. So as we lower the temperature, the water molecules stop moving around quite so much and they move a little bit closer together and it gets a little more dense. Strangely though, when it freezes, they move back apart from each other and ice is less dense than water, which is still seems weird to me, but it's true. So we're going to use the mass to determine our volumes. So let's clear that. There we go. All right. So in our 10 mil graduated cylinder, we're going to try and put 7 mils of water. And this is why I would suggest using the transfer pipette, because like I said, trying to pour 7 mils of water in here is going to be really hard. So what I do is I just take my glass of distilled water. Here's my glass of distilled water. And I just draw it up with the transfer pipette and then put it in here. It also keeps me from getting water on the sides. Because if I get water on the side, well, obviously that's going to add to the mass, but it doesn't really add to the volume. So if I have bubbles or if I have water on the side, I want to tap those down. Then when I get close to 7, I really want to stick my head in there. All right, so now I'm pretty close to 7. So I'm going to get down with the level. I'm going to get down to the level of my graduated cylinder and put in 7. There we go. Now, what should I have done before I did this?
Measure the mass of the cup.
There you go. Yeah, measure the mass of my graduated cylinder. Should have done that first. But what I can do is measure the mass of it full and then empty it and then measure that mass. But I should have done it the other way. So full, I've got 18.04 grams. So 18.04 grams full. Then I'm going to empty it and get all the water out as best I can. Okay, looks like it's
Professor?
all out. Yes.
So what we had to do is the 7 milliliters from here, from the cylinder transfer and we're into the cup on the scale?
No. So we measure the mass of the empty cylinder, record that, and then we put precisely 7 mils of water in here.
Okay.
Getting down, and then we measure the mass of it when it's full. I did it the opposite way. So, nice. So empty, it is 11.04 grams. MT. So the difference is going to be the mass of my water. And so nicely for me, the mass of the water turns out to be 7.00 grams, which is pretty darn close to what it should be, right? Should be around 7. Now, how am I going to convert? So my estimated volume is 7 mils. How do I determine what the actual volume is? Because we can do that. We can actually measure, or we can determine, we can calculate what the actual volume of water was in that cylinder. How do we do that?
Subtract.
What do we subtract?
Convert.
18.04 minus 11.04.
Mm-hmm. So that gives me 7 grams. So that's the mass of the water mass. But that's a mass. How do I want to know what the volume is. How do I do that?
Oh, you would divide by the density?
Right. I basically, I take the mass and I convert it to a volume using the density, precisely. But how do I know what the density is?
Using the temperature of the water?
There you go. Right. So in table 3, let me do table 3 in, clear all the drawings. So this comes from the lab manual. So I'm going to go down to, there's activity 1, 2, and 3. Table 2, oh, sorry, not table 3. Table dose, table 2.
Professor?
Yes.
This is what my scale shows, like the number. Why is that?
I can't see what you're pointing out, David.
Now, can you see?
No.
Oh, because it's, okay, give me 1 second.
It's because this background you're using. Yeah, it's.
Oh, I see.
Yeah.
Give me 1 second.
Still can't see.
There?
No, still can't see it. What does it say? Just tell me what it says.
It says 0 LD.
0 LD. Oh, because it's not, that just means it needs to be flat. It needs to be flat on a flat surface.
It's on my desk.
Okay, so put it flat down and then hit M for the mode until you get to G for grams.
All right.
Okay. And then hit the tare button, or T for tare. Does it say 0 now?
It goes to minus and then goes to 0 and minus again.
Yeah. So just hit. Yeah. So it's varying a little bit because you're probably standing over it and breathing on it or whatever. I mean, it'll do that.
And
so
then
just
when I place it on top, it says 0-LD.
0-LD. What are you putting on it? 0-LD. I don't know what that means. I mean, that should not be over the limit. There should be a limit of like 100 grams on that. But the minute you put anything on it, it says that?
Yep.
Doesn't matter what it is. If you put it on, you get 0 LD.
Yeah.
And you sure it's like grams you selected?
Yes, it is.
Yeah, I don't know what that means. Maybe look in there should be like a little manual there. Yeah, mine's slightly different, so I don't know. LD, yeah, it means there's something wrong with it. We might need to replace your scale, your balance.
Okay, thank you.
So you're just getting LD every time, LD,
Yeah.
LD. Weird. So if you put it to ounces, do you get the same thing?
Let me see. Yes, it does.
Oh, that's bizarre. Yeah, maybe like I try different batteries in it, or yeah, if that doesn't work, then yeah, maybe we just swap it out for another one.
I'm gonna try to recalibrate it maybe.
Yeah, that's Yeah, I don't, LD, I'm trying to think of what that could possibly mean. Yeah, look in the owner's manual. I mean, it's not going to be, it's not going to be a very elaborate owner's manual, believe me. But that generally means out of range, but I don't think it should be.
All right, thank you.
All right, man, yeah. Okay, so table 2. Table 2 in the lab manual will give you the densities providing your temperatures between 18 and 27. Mine is less than 18, so I'm going to have to look mine up. But if it's between 18 and 28 degrees, to figure it out, we go to the temperature. So we look at the temperature here. Let's say if your temperature was, let's say it was 19.7 degrees C. So you go down to 19, and then you go over 1, 2, 3, 4, 5, 6, 7. And that would be the density of the water in grams per milliliter. And so notice they're all pretty close to 1, right? There's not a whole huge difference between 0.9986 at 18 degrees and 0.9983 at 19.7 degrees, but they are different. So this is a systematic error we can correct for because we know what the densities of water are at all these different temperatures. And so we can correct for that. And so that basically eliminates a source of error in our experiment. And like I mentioned before, when you're writing your, you write your procedure, you write your results, and then you write what your conclusions are. Part of your conclusions are what were your sources of error. And so this would be eliminating one of those sources of error. Because if everyone just used 1.0 grams per mil, that'd be fine. We'd all get pretty close to the right answer, but it wouldn't be as precise. So this helps eliminate some of that error. So does everyone see how you use the table? And if you can't use it, like for instance, I can't use the table. So I'm just going to look up what the density of water is at 15.6 degrees. See, I'll just look that up. Just go density of water, 15.6 degrees C, and it'll bang, it'll tell you what it is. That's the nice thing. Like 30 years ago, we didn't have to do that. We'd have to look up a table in a book. So we don't have to do that anymore, which is pretty sweet. Okay, so let me go back.
Question?
Yes.
What would you look at?
Can't hear you.
Oh, what would you look up again?
Oh, the density. If the density of water. If for instance, your temperature is less than 18, which it very well be, it's the Bay Area, right? I doubt it's more than 27, unless you're living in an old folks home. If your temperature is less than 18, just Google density of water, whatever your temperature is, Celsius, and then boom, you'll just get an answer. And then use that density to do your calculations, okay? So let's go back to our activity. So we did 7 mils in our graduated cylinder. So then next we want to do 24 mils. Cami, get away from me. So we're going to do 24 in our 50 mil graduated cylinder. So we'll do that the same way. Just measure the mass before. So the mass of my graduated cylinder is 29.37. 29.37 grams. Empty. So then I want to put 24 mils of water in it. So again, I'm going to use I don't want to make a big mess. So I'm going to use my transfer pipette. Each time it transfers about 3 mils, or you can just pour it up to 20. That's fine. Now remember, if you have any bubbles You want to tap those out. And if you have any drops of water on the side, you want to tap that as well. Because that's going to affect, the water on the side is going to affect the mass, and the bubbles are going to affect the volume. So I'm just going to tap this till everything comes down. Okay, I've got some bubbles in here, so I want to get rid of those. You can also just tap it. Good way to do it is get a pencil or a pen and just tap the side. That's a good way to get rid of bubbles. Or it used to be anyway. All right, there we go. Then like before, I just get down. A little tiny bit less than 23. So I'm going to get it up to 24. That looks pretty good. And then I'm going to take the mass of it again. And my mass this time, 53.75 grams full. So that means that my 24 mils of water equals, I'll just subtract the difference. So 53.75 minus 29.37. 24.38 grams. Now again, I am going to convert this to a volume using the density. And when I convert that to the density, I'll look at my error in that. Now again, that's partially going to be, and what I'm curious about, I wonder if my relative error is going to be the same or more or less than with the 10. You probably have to repeat this like 3 or 4 times to get an actually good result. Because if we're just doing this once, any experiment you do just once is not really an experiment. You'd be usually, hey, when I worked in the lab at UCLA, I would always do my experiments 4 times. And then if 3 of the results were really close, I'd keep those. And if one was different, I'd throw it away because something weird happened. So that's would be when you would calculate your deviance. And if 3 of them were really close and one was a lot different, you toss that. So if you do something 4 times and one of them you toss out, what's that one you toss out called? Anyone know what that's called? That measurement?
Outlier?
An outlier, excellent. Yeah, so we avoid using outliers because if we, basically it means we did one of those things wrong. We don't know, I might have done something wrong. The chemical I used was like wrong, something was wrong. But if we include that in our calculations, it screws up our calculations. So then it moves all of the errors. All of the errors become bigger because of that one thing. Well, if we can figure out that that one thing is screwed up, we get rid of it and our errors are shrunk and we get closer to the actual answer. So the next one we're going to use is the flask. Now this one is going to be really tricky because like I said, when you look at it, there's only 2 measurements on it, 12.5 and 25. How are we going to determine what's 17? Because, so 17 should be somewhere in between those 2, but how close? I don't really know. So when you do that one, I'm pretty sure that one's going to have, do you think it's going to have more error or less error than the 2 graduated cylinders?
More.
It's got to be more, right? I mean, it's definitely going to be more. And then finally, we're going to be trying to measure 35 mils of water in a 250 mil beaker. Now that doesn't sound like such a bad idea, but what's the very first measurement on here? But look at your own beaker. What's the very first measurement?
50.
50, right. So basically, when we're trying to measure 7 in our 10 mil, there's measurements above and there's measurements below. So that helps us determine whether we're over 7 or under 7. And the same thing is true with our 50. When we're measuring 24, we have measurements below 24, we have measurements above 24. And even with the ridiculous task of trying to measure 17 mils in a flask, well, at least we have something that's smaller than 17 and something that's bigger than 17. However, now we have no way of knowing whether we've gone over a particular number or not. All we're going to know is that it's less than 50. That's it. That's all we're going to know. So you might be able to, if you were like to, maybe you want to measure these with a ruler and then see which one is halfway between 50 and the base. That'll give you like a rough idea of where 25 is, but still, that's going to be a hardcore estimate. Basically flying blind on this one. So
are we able to use this one to do 35?
No, the whole point is to show you, yeah, if we wanted to measure 35 mils accurately, yeah, we would have used the 50 mil cylinder. But the whole point of the exercise is that we're using a crappy way to measure 35 mils. And the exercise is to show you how much crappier it is than using the graduated cylinder. Because what the whole point is to measure the standard deviation, like basically what is the accuracy of each one of these things. And I think what we're supposed to find is that the two cylinders have approximately the same accuracy, the flask less, and then the beaker even less. That's probably what everyone's going to do. Everyone's going to get slightly different results. I mean, some people might be like eagle-eyed or have like, the third vision or through their third eye or something where they can, make really good estimates when the rest of us can't. But so we'll all get slightly different results, but I can guarantee you that everyone's results for flask and beaker are going to be less accurate than the two cylinders. And that's basically what we're going to be looking for in the reports.
Oh, Professor?
Yeah.
So we would just estimate. We don't use the other flask.
Can't hear you.
We would just estimate and with our eyes.
Yeah, that's all you can do. I mean, with the two cylinders, you can actually get a fairly accurate measure by getting down to that level and looking at the meniscus and everything. That's all well and good, but with the flask, you don't have nearly as many measurements to go off of. There's only two. And basically all you know is that it's going to be about halfway in between them. So you may be able to get fairly close with that. Not nearly as accurate as Arissa pointed out if you use the graduated cylinder. But the beaker, basically you're flying by the seat of your pants because there are no measurements of 35 here, none. So you're on your own. Some people are going to get it close, some people aren't, but it's not your fault because this isn't designed to measure 35 mils. And that will be the point of the exercise, to show you that we don't measure small volumes with this. We do not do that. And there's a reason why we don't do that, because your error analysis is going to show you that it's a crappy way to measure it. Ooh, what's someone's posted? Oh, someone's posted on the chat. Okay. So use the cylinder to fill up the flask and beaker. Ah, yes, don't do that. If you've measured out precisely 35 mils in the cylinder and then poured it into the beaker, yeah, that wasn't the point of the exercise. Because basically what you're doing is using the cylinder to do the measuring. We want to actually use the beaker to do the measuring. One thing I want to point out to you if you look on the top, so look at the very top of the graduated cylinder. You'll see some writing. It's kind of hard to see over the screen, but it'll say who made it, ESCO, I think, or something. And then it'll say 10, comma, or 10 colon 0.2. So it tells you the volume of it and what each check mark is, what the measurements are. And then below it, it says TC, TD, 20 degrees C. Well, we know what the 20 degrees C means. What do you think TD and TC means? TD, TC.
Density and something with density in Celsius.
No, that's a good guess though. So we know what the temperature is. It says 2, so I'll give you a hint. T stands for 2. It does something at 20 degrees Celsius, which is sort of basically what we usually think of as like generally room temperature. This will do something. It will do 2 things at 20 degrees C. One of them is a D and one of them is a C. We'll start with the C. What do we want this thing to do? We want it to hold something, right? We want to, what's another word for holding something?
Contain.
Contain, bingo. So basically this thing is designed to contain 10 mils at 20 degrees C. I keep putting the, so it's 2, TC means to contain 10 mils at 20 degrees Celsius. It also will do something else. It will also D 10 mils of water at 20 degrees C. What's the other thing we will use this for? So it'll hold 10 mils of water. What else can we do with the water after we've put it in here?
Measure.
That's the contain part. That's the contain part. We've measured 10 mils. Now, after we've measured it, what do we do with it generally?
Deliver.
Bingo. Man, you guys are sharp today. Yes, deliver. It will deliver. So it's one of the few things that is designed to both hold a particular volume, and then once you've measured it, you pour it out, it will deliver that same volume. So that's why we don't use this to measure the 35 mils and then deliver it to the beaker, because that is going to be pretty darn accurate, because basically we're using the 50 mil graduated cylinder to contain and then to deliver 35 mils. What we actually want to figure out is if we were to use this to contain, and notice on this one, there's no writing TC or TD on it because this is not a measuring device. The other two are. And you will see that on measuring devices. Measuring devices will either be to contain and to deliver. Some are just to contain and some are just to deliver. It depends on what kind of instrument it is. So that's why we don't want to use the beaker. I mean, that's why we use the beaker to measure, because we want to see how crappy it is in real life.
How do you measure 17 ml on the flask again? Do you measure on something else?
No, you use the flask. No, the whole point is you're going to do a pretty crappy job of estimating 17 mils.
All right.
Yeah, don't worry if you do your measurements and you go, oh my God, that's nowhere close to 17 mils. Yeah, that's the point, because this also, we see it's got writing on it too. Nowhere does it say TC or TD on it, because this is also not a measuring device. It just isn't. So the only reason these two measurements are on here is to give us an idea of like it's half full or it's full. That's it. So we don't use it. We don't use it to measure. We use it to hold things for reactions. So let's go to. Oh yes, go ahead.
Oh, I don't know if you explained it, but How
I
would
may have
we
explained it badly.
how would we figure out low volume interval and high volume interval?
Oh, yes. Excellent point. Yeah, the high and low volume interval. That is basically what you think would be the maximum volume you're looking at or the minimum volume you're looking at, just by examining the container it's in. For instance, I'm looking at my 24 mils in my 50 mil cylinder, and I'm looking at this thing, and I'm thinking, because each one of those check marks, each one of those checks is 1 mil, right? So I'm looking at it, I'm getting down, I'm checking it out, and I can pretty much determine whether or not it's halfway in between or right on, and maybe even a little more accurately than that. So I would probably estimate for this that my lowest could possibly be like 23.8 maybe, and the maximum could be like maybe 24.2, but it's not going to be any much more than that, because I can easily tell whether or not the meniscus is less than halfway or more than halfway in between those two marks. So that would be my range for this. Now your range for the flask is going to be huge. Like, can you really, like, if you filled it up like about halfway in between those things, could you say, you could probably say that, well, it's going to be more than 13 and less than 19, and maybe more than 14 and less than 23. But then it's just basically, how accurate do you think you can get? What's the lowest you think it could be? What's the lowest volume you think it's possible? And what's the highest volume you think is possible? And that's more or less up to you as to what you think, based on how accurately you can determine it. Do you understand what we're trying to do with that?
Yes, I understand.
Yeah. So basically, it's just a way of because there are internal divisions in the two cylinders, and there really aren't for the flask. There is an internal division, but it's really big, and for the beaker, there's no internal divisions at all. So basically, our uncertainty for or interval uncertainty for the volume uncertainty is going to start small and then get huge. And basically, what we're going to try and see is your estimate inside that inside your basically you're giving an error estimate. So you're saying, like, you know, it's going to be 35 mils plus or minus 10 maybe. And then you're actually going to measure what the actual mass of that water is and see if are you right? Is it within that interval? And I bet it is. Especially if you give yourself a huge interval. If you say it's plus or minus 35, then yeah, I'm pretty sure you're going to probably get that. But you should be able to measure it more accurately than that. Let's have a look at the last table. So we have our empty, mass filled, mass of the water. What you think the lowest volume possible is based on your eyeballing of it. What's the highest it could be? And that difference will give you your uncertainty, okay? Then we're finally going to figure out what the actual volume is in each one of these scenarios. So we have our 10 mil cylinder, 50 mil cylinder, the flask, and the beaker. You'll record what the temperature of your water is. Here it's just given as 25, obviously whatever the temperature of the water is in your room. Look up the density. You're probably going to have to look up the density because Yeah, this is Carolina Scientific. They're in North Carolina. They're probably not used to, you know, days of 15 degrees outside or in your house. It's always warmer there. So we're probably going to have to look up the density of water, and then you're going to calculate the volumes. Okay, and then we'll see whether that volume is within the error you predicted. And then that's basically it. And then I think there is a post-lab question. Calculated volume. Is there a post-lab? There isn't a post-lab question. So unless there is one, yeah, you just basically go ahead, do all the calculations from the table, and then in your conclusions, you would basically tell us in your report, is the volume that you calculate within the error you suggested? And if it is, why? And if it isn't, why not?
Can I ask a question?
No. Yes, of course.
In that first row where it says massive water and activity 2, are we basically just putting in the grams for the full one and then minus the grams for the empty one?
Exactly.
Okay.
Yeah.
It's gonna be like
you're just carrying it over from the last table. Yeah.
Okay, so it's gonna be like around 10 milliliters. Oh wait, no, it's gonna be
it
like
should be around 7.
Yeah. Okay.
And then
Gotcha.
50 should be around 24, and then the Erlenmeyer flash should be around 17, and then the last one should be around 35. Around, I mean, you know, you could the last two are probably going to be way off.
Could you give an example of like one of the two intervals, like using one of your?
Oh, sure. So the ones on the cylinders are going to be fairly easy to calculate, because when you look at the gradations, at the markings, basically it's pretty easy to tell whether it's halfway in between the two markings. So I'll just write it down here. So I'm going to, let's get a whiteboard going here. All right, so I've got so here's my graduated cylinder, and this is 10, this is 9, then it has 1, 2, 3, 4, 5 markings in between, right? So this would be 9.2, 0.4, 0.6, 0.8. So if you were to measure something that was here, you could be pretty sure that you know it's not 9, so it's more than 9, and you know it's less than 9.2. And if you were to look real close, would you say that this is more than halfway between or less than halfway between?
Less.
Or
yeah, well, see, that's, some people would say more, some people would say less. So you can pretty much have a pretty good idea that it's either 0.1. If it's exactly halfway between, it's 0.1. If it's slightly less than that, it's a little less than that. But probably 0.1 is about as good as you're going to do. So I would say if that was right there, I would say my interval is probably, it's between 9 and 9.2. So that would be, my interval would be, usually my interval is either the difference in those two tick marks or slightly less than that. I mean, if there's a big difference between them, I could probably say it might even be half of that. But this is a pretty good indication of what my interval would be.
So then would you subtract and then divide by 2?
I think that's what is that what in the manual, is that what they suggest you do?
Yeah.
On the manual, it's suggested to use the gradation lines or graduation lines. So can we just use those, or should we be more specific?
Well, have a look. I mean, if you think, I mean, for instance, the gradation lines in the 10 mil are a lot closer together than they are at the 50. There's the same number of gradations, but there's a bigger distance in between them. So if I have 49 and 50, whoops, and 1, 2, 3, 4, 5, and it's here, I probably have a better idea that it's closer to 49.14, something like that. Because basically, I know it's more than 49.1 because it's more than halfway. And so this is a real estimate, you know? So my gradation, my high and low estimate might be relatively smaller on the 50 mil than it is on the 10, just because the tick marks are further apart in the 50. So you really have to look at it and think to yourself, I know that, you know, just look at it and see where the line is. If it's right on 7 and you know that it's not 7.05 and it's not 6.95, then that difference is 0.1 rather than 0.2. That's even more accurate. It's just, how confident are you that that 7 mils is exactly on the line? Maybe it's a little bit less, maybe it's a little bit more. So, but if it's exactly on it and you can say to yourself, yeah, that's exactly on it, and there's no bubbles and there's nothing else, then maybe your confidence interval goes down even more. So you really have to look at it to give I can't tell you what your estimate's going to be. Everyone's is going to be slightly different.
Thank you.
Yeah, it's kind of hard because it doesn't really tell you what to do with that one, right? You're sort of on your own. Like, I don't know what my high and low estimate would be. Everyone's is going to be slightly different. That doesn't mean you're going to be wrong. It's just going to be different. Somebody else may have the greatest confidence that, hey, I'm the greatest measure of volume in the world, and I can get it really, really precise. Well, maybe you can't. I don't know. Any other questions?
So for this one, would you just do the best estimate since there's no tick marks?
That one you're on your own. Yeah, there's no, basically it's 12. So halfway between 12 and a half and 25 is 17.25, right? That's right in between. So basically what you're looking for is you're going to want to get it slightly less than halfway. That's it. That's the best I could do for you. And so then you have to sort of looking at it, say, well, if I had to judge what's the minimum this could be and what's the maximum this could be, and then that's going to be your interval, and it's going to be pretty big with that one, right? That's no the slight on you. That's because this is a crappy way to measure volume, and that is the whole point. It's not that you can't, shame on you, you can't measure volume in a flask. Well, nobody can because they're not supposed to. So if you're way off, not a problem. That's the point of the exercise.
Hey, for data table 1, the deviations, some of them are going to be negative, right? Like you're putting the negative symbol?
Yes.
All right.
Yes.
So,
yeah, some of them are going to be negative. So when you add them together, you may come out to 0.
So my average
notice when you do the standard deviation, that's why with standard deviation they're all squared. So that eliminates negative values. But when you're just calculating the deviation, yeah, some are going to be positive, some are going to be negative.
My
Yeah.
average has 4 significant figures. Do I just round it to 3?
I bet it doesn't. I bet it has 1.
No, for the mass.
Yes, the mass will have 4 significant figures. Yes.
So you just put it right. All right.
Your deviation will not have 4 significant digits.
I have another question about.
Okay.
So let's say, for example, all of the masses for the cups we measured has 4 significant figures, but then when we do the average, we get 5 sig figs. So should we round that to 4, or should we keep all of them when we're doing the average?
Sorry, when do you get 5 sig figs?
When I'm finding the average.
That's a good point. No, you would get 4, right? Because if you take 4, yeah, because first you add them. Right, when you add them all together. So if you add them all together, you get 5, and then you divide by 4. Yeah, I think you're in the same number of digits. That's a really good question. I think you would have the same number of digits. But that's a really good question. I'm going to have to look at that. Because, yeah, when we add numbers together, if we add a lot of numbers together, we increase our significant digits. Because, and then when we divide, man, that's a really good question. Yeah, let me think about that one. Because you're right, the average will have 5 significant digits, but if we divide by the number of observations, that's a count. That is not a measured number. So do we keep the 5 significant digits? I think we do. Now that I think about it, I think we do keep the 5 significant digits.
Okay.
That's a good question. I'm going to look into that, but I think, yeah, because we've learned that when you add numbers together, when you add them together, the significant digits beyond the decimal point don't change, but the numbers before the decimal point will, because they'll just keep getting bigger and bigger and bigger. So when we divide, I think we keep the significant digits. So yeah, that's a good point. Yeah, best question today. I gotta say, it's a head scratcher. Maybe think about that one. I love it. Any other questions before we call it a day? Now remember, yeah. So you don't have to, take all your measurements and then you can do your calculations whenever, obviously. But hopefully you've got everything you need to finish the experiment now. If you have any questions about the reports, yeah, just drop me a line or come to group meeting. I keep saying that. Come to office hours. I can answer then too. Okay, is everyone cool and groovy?
Yeah, thank you.